Welcome back. So the next example I want to look at is number, which one did I say? I want to do number 137. So I wanted to make sure that we look at a trig one. So with this one, we have h of x equals the tangent of 2x. So the first thing that I want to do is I want to figure out what the period of this thing would be. And to do that, I'm going to have to use a formula that is back in section 1.3. So if you don't remember how to find the period and amplitude and all that of a trigonometric function, there is some information about it in the chapter 1 of this book. So to find the period, remember the period is going to be, come on. Is the formula pi over the absolute value of b. In this case, our b is 2. So this is going to be pi over the absolute value of 2, which is, of course, pi over 2. So that's our period. I do want to look at a box right quick. So just write that down. Period is going to be pi over 2. Let me clear this out because I want to go back up in your book here. So I'm going to look at page 187, which, you know, no book pages online. So number 187. Oh. So here's your composite function theorem. So if f of x is continuous at L and the limit as x approaches a of g of x equals L, then the limit as x approaches a of f of g of x equals the f times the limit as x approaches a of g of x, so f times L. Okay, so here's kind of an example that you guys can look through, but basically what they're saying here is they go through and they figure out what, or they find that you've got two composite functions. One's cosine of x, and the other one is x minus pi over 2. Ours would be tangent and 2x, or tangent of x and 2x, that would be ours. And so we go through and we're going to kind of do something very similar to this for ours. And then continuity of trigonometric functions. Trigonometric functions are continuous over their entire domains. So just two pieces of information I wanted to share with you. Here is a beautiful proof if you would like to look through that a little bit more in depthly. But basically what I want to do here is I want to figure out, so the thing about tangent is tangent does have asymptotes, right? Tangent does this. So we've got that nice little squiggle. So in tangent has asymptotes very regularly. So what I need to do is I do know that I'm going to have infinite discontinuities just because that's what the graph of tangent looks like. If we want to make sure that we know what the graph of tangent looks like, you can say f of x equals, in our case, it was tangent of 2x. So notice lots and lots and lots of asymptotes. So what I'm after is I'm after these asymptotes. And these asymptotes are based upon the period. So what I'm going to do is I'm going to use that idea of the period that we just come up with. And I'm going to say, okay, so our period, we got let's just do a new share. Let's do a whiteboard. There we go. So I got room to write. I'll tell you what, me and Zoomer, we're having some issues right now. We're not talking real well. Try this again. Share a whiteboard. Clear this out. So we said our period was going to be pi over 2. So now what I'm going to do is I'm going to use that 2x that we had here, and I'm going to set our period on either side of that. So we've got negative pi over 2 is less than 2x is less than pi over 2. And now I'm going to solve this thing for x. So I'm going to divide both sides by 2. Because we're trying to get that 2 off the x, because I'd like to see just what x is going to be. So this is going to be negative pi over 4 is less than x is less than pi over 4. So what that means is that we are going to have asymptotes at every single, or starting at pi over 4. So negative pi over 4 to pi over 4 is where our first two asymptotes are going to be. So I'm going to go, and our period's pi over 2. So that means the next asymptote is going to be whatever pi over 4 plus pi over 2 is, or whatever negative pi over 4 minus pi over 2 is. So to state it, we know it's going to be an infinite discontinuity. We're going to have infinite discontinuities. At, and that's going to occur at pi over 4 plus or minus n pi over 2, where n is any integer. Again, guys, this relies heavily on you remembering how to do your trig stuff. So if you're having a hard time seeing the trig stuff, make sure that you go through and do a really good, solid review of that. All right, so what do I want to go from here? See what else we can do. I think we need to talk about, I don't think we've actually looked at a whole example, so I need to show you a whole. Let's do number 139. So on number 139, they do ask us to decide if the function I think that's supposed to be decide if the function is continuous at the given point. If it is discontinuous, what type of discontinuity is it? So here, 139, we've got f of x equals 2x squared minus 5x plus 3 over x minus 1 at x equals 1. Now, I do have a feeling that this one has a hole in it. Guys, remember, holes crop up when you can do some factoring on the top and the bottom. Or a lot of times those crop up when you can do that factoring on the top and the bottom, and something will cancel out. So I do feel like this one's probably going to have a hole. Just to make sure, though, let's go through and actually factor. So I'm going to have f of x equals, if I factor 2x squared minus 5x plus 3, that's going to end up giving me x minus 1 over 2x minus 3 over, and then of course the x minus 1, and there we see that hole because those two things would cancel out. So we do have a hole at x equals 1. And so that means that we have a removable, right? A hole is a removable discontinuity at x equals 1. And one of the reasons a hole is considered to be a removable discontinuity is we could set up a piecewise defined function and define a value to fit that hole. So that's why it's considered to be a removable discontinuity. All right. Trying to figure out. Let's do 141. So number 141, we have a piecewise defined function. So we've got g of u equals 6u squared plus u minus 2 over 2u minus 1 if u is not equal to 1/2, and then 7/2 if u is equal to 1/2. I think this one may do exactly what we just talked about in the previous example. So looking at that top one, anytime I see polynomials, the first thing I want to do is try to factor. That's what I'm going to do. So for the top one here, we've got g of u equals, doesn't look like a u, but that's okay, 6u squared plus u minus 2. That is going to factor out to be 2u minus 1, 3u plus 2, over, now the bottom of course is not going to change, that's going to be 2u minus 1, and my goodness, look there is a hole. So that hole is whatever 2u minus 1 equals 0 whatever u equals in that particular statement. So in that case, if I was to set 2u minus 1 equal to 0, add 1 divided by 2, we do end up with, we have a hole at u equals 1/2, which is probably why they said we're not going to be the top function if u is equal to 1/2. So what I'm curious is going on here is I'm curious if we're going to get the same thing if we take, so are we approaching the same thing from both sides? So I would really like to take the limit from both sides. So what happens if I plug in a half? So let's actually go to Desmos here. I want to look at Desmos. So let me clear this out. Just keep that wrote down somewhere. Come on. I'm only going to graph the top one because I think I've got a pretty good idea of what's going on here. And I'll kind of walk you through it. So 6u squared. You're probably yelling at your screen because it takes me so long to type these things in, and that's okay. I'm yelling on the inside too. And that was over 2u minus 1. Okay, so it doesn't look like a lot's happening here, right? It looks like I've got a straight line, but again, remember Desmos can't show you the holes. So I think that if we do a table here, let's make this let's make this u1. Guys, remember, you have to be very, very careful with these variables because if these variables don't match up, Desmos gets mad. G of u1. Okay, so I'm going to type in 7/2 here. And, 7/2, 1/2, my goodness. I'm going to type in 1/2. Where did I even get 7/2? Oh, that's what it was equal to. So I do get this undefined. So something weird is happening at 1/2. So what I would kind of like to do is I kind of like to see what's happening on either side of 1/2. So let's come down here and I'm going to do, so 1/2 is 0.5. So let's do 0.49999999999. Oh, no, I just made it go away. Why would I do that? Oh, let's do undo. So it looks like we're heading towards 3.5. Let's see. I'm going to do 5.000000. Nope. I'm not either. I'm going to do 0.500000011. So it does look like I'm heading towards 3.5 on either side. So I am approaching the same thing. It's just I've got a hole at 2, 2 comma 3.5. Now 3.5, another way of writing 3.5 is actually 7/2, right? So let's go back to our book here. So our book, notice what they have done. They are saying, oh, if u is 1/2, let's fill that hole in as 7/2. So they are specifically picking the one place where we have a hole in the graph, and then through this idea of piecewise defined functions, they're going to fill that hole in. So it actually turns out, because we're approaching the same thing from the left and the right, and then where I had a hole, it's defined. So I'm using those 3 conditions that was given to me a couple of pages ago. That means that this thing is going to be continuous. So this thing is continuous even though it has a hole. And that's just because of the fact that all the math works out. That's a pretty cool one to look at. Trying to see if there's anything else that's even remotely entertaining here for these. No, I think I'll stop the video here and we'll pick up with a little bit different idea. So I'll catch you in that video.